Do you have millions of rows of data but need your SQL query to run fast? I've got a query on a table with about 10 million rows in it, and I want the query to run in under 3 seconds so that users don't get annoyed with how long it's taking. I will be using this dataset of Steam game reviews, which is available on Kaggle and has over 100 million rows in a CSV file. From this file, I'll create a subset of data that has 10 million rows. I've downloaded this in a zip file which is 17 gigabytes. Once the download is done, I'll extract it and have a CSV file. This CSV file has about 100 million rows. For this example, we only want 10 million. To do this, I can use a terminal command to extract a specific number of lines. First, I'll open the terminal. Then I'll change to the directory that the downloaded CSV file is in. In this folder, I'll run a command called head, which reads part of a file. The -n specifies the number of rows, which I specify as 10 million. Then we have the file name, which is allreviews.csv. Then we have an arrow which indicates we want to send the output somewhere else, which is this reviews10m CSV file. I'll run this command, and after a moment the prompt appears. The file has been generated. We can see the file here in Finder. Let's import this into MySQL. In this video, I'll be using MySQL. There are other databases I can use, and the next video I'll create will be with another database so we can see how it compares. Let's import the data. First, I'll create a new table to store the data from the file. These data types and sizes have worked for me for the import. You can find the SQL scripts for this video at the link in the description. I'll use the load data in file command here, as I found that this is faster than the table data import wizard. To enable this for my session, I'll have to set this global value first. Now I can run this load data in file command, which imports the file into the table I have created. After a little while, this has completed. On my computer, which is a 2021 MacBook Pro with an M1 chip and 16 GB of RAM, it took 126 seconds, or about 2 minutes. The warnings here are all to do with data being truncated for the review column, meaning some reviews are more than 8,000 characters. However, the data has still been loaded in. I also had to do a find and replace on this CSV file, as reviews with backslashes in them were causing the import to break. I'll add the commands I used in the description. Let's run some quick queries on this table. How many rows do we have? I'll run this select count query, and we can see we have 9,999,999 rows. This is one less than 10 million because our file had 10 million but included a column header. What does the data look like? I'll run a select star query and limit it to just 100 rows so we can see all of the columns but only a small number of rows. We can see our columns here. We have a recommendation ID, which is a unique ID for the row, some app ID, the name of the game being reviewed, the Steam ID of the author of this review, some stats about the author, the language of the review, and the actual review text. We also have the timestamp of when the review was created and updated, which is actually in something called epoch time. We then have some information about votes for the review, comments, and other attributes. So that's what's in the table. What do we want to analyze in the table? Let's say we're building a new report on a web page on the Steam website that looks at this data. We want to see the most popular reviews, but we only want to see the reviews from the top 10% of authors. An author can be in the top 10% if they are in the top 10% of games owned, total playtime, or the most reviews. We also only want to see reviews in English and those that have at least one upvote. I've already written this query, which we can see here. We select a couple of columns from this reviews table. We use the function from Unix time to convert the created date time into something we can understand. Our where clause has some conditions in it. We filter on records where the author ID is in the top 10% of games owned. We calculate this by using the %rank function. This will return a decimal value of 0 to 1, with 0 being the top record and 1 being the bottom. A record is in the top 10% if this function returns a value of less than or equal to 1. That's what the subquery does. We have two similar subqueries here, each of them calculating the percentage on different values. The subqueries are checked using an OR keyword because an author can match any of these criteria. Finally, we filter on votes up and language, then order by the votes up. Let's run the query. We wait, and it is done. The results are shown here. How long did that take? Oh, about 186 seconds. That's way too long. We don't want users to wait 3 minutes for a page to load. How can we get this to run faster? Let's start with the execution plan. I'll display this by clicking here. This is the execution plan for this query. We can see the total cost is 1,767,665. The query runs 3 separate queries here, which are each of our subqueries. It uses a full table scan on each of them. The results are then combined, and then we have an order by here, and then the final step to display the data. What can we do? The first thing I try when looking to improve the performance is to add indexes. I'll start by adding indexes to columns used in the where clause and those used to join between tables. So for us, that means one index on votes up and language and another on the author Steam ID. I'll run these commands and the indexes are created. Let's check the execution plan. We can see that the cost has changed to about 1.9 million. The subqueries still have a full table scan. I'll run the main query again, which has now been completed. It took 184 seconds. So the indexes haven't helped to improve this query. In the execution plan, we saw that one of the steps that took some time was an order by. Is there a way we can use an index to help with this? Many databases, including MySQL, have the concept of using an index to help with ordering data, as the database can use the index to find the rows when ordering, instead of sorting the table. We can create an index on this column, and we can actually create what's called a descending index. This means the data in the index is in descending order, just like our query, so hopefully it will be used. We run this statement and the index is created. Let's check the main query again. We can see the execution plan shows a cost of about 1.9 million, which is the same as before. The order by step has not changed. Let's run the query. We run it and it has completed in 181 seconds. We have the same results, but the runtime is still pretty slow. What else can we do? Well, another approach to improving the performance of a query is to change how it is written, or change the structure of it. Is there anything in this query that can be written in a different way? Well, I think there is. In the execution plan, we saw there are 3 separate queries run as subqueries. And in our query here, we can see the 3 subqueries. They all query the same table. They are all returning the author Steam ID, and they have a slightly different calculation for the percentage rank. Could we update our query to use a single subquery to check for all 3 of these rules, rather than 3 separate subqueries? Let's try that. We'll need to add all 3 calculations into the one subquery, and then update the where clause to check if any of these columns are less than 0.1. Our query is now ready. Let's check the execution plan. We can do this and see the cost is about 4.9 million, which is more than double the previous query. We can also see that there is now only one subquery, which should have helped our performance. Let's run the query. We run it and it has completed in 272 seconds. That's worse than the previous query. What else can we do? Another tactic we can use is performing some calculations outside of our main query. What am I talking about? Well, rather than calculating the top 10 authors of this criteria each time we run the query, wouldn't it be good if we had a predefined list of the top 10 authors? And then all we need to do is check if our review author is in this list. This means the percentage calculations can be in one query, and then our query comes next. Let's try this. We can create a new temporary table called top authors. We'll create this from a select query, which we get from the main query. We'll select the author Steam ID from our subquery, which gets all of the author IDs and the percentage ranks. We can run this query and it has completed in 176 seconds. Let's update the main query to select from this table instead of running the calculation. Our subquery selects from the top authors table and we only select the author Steam ID. Our query is now updated. We check the execution plan and it shows an error. Why is that? Let's try to run the main query. We do this and we get an error about missing columns. This has happened because we are trying to filter on the ranking columns, but they are not columns shown in the temporary table. This can be fixed easily by adding them to the outer select when we create the temp table. Let's do that. First, we drop the temp table. Then we add the 3 ranking columns to the outer select query. We can run this create temp table statement and it completes in 178 seconds. Let's have a look at our query. We added this temp table which calculates the percentage rank in a few ways. In our query, we filter out rows where these rank values are greater than 0.1. Then we match to the author's ID. So in this query, I believe the database will be loading all of the data from the temp table and then doing the filter to exclude these rows. How many rows are being brought back and how many are then being excluded? Let's find out. We can select the count of rows in the temp table, which gives us just under 10 million. Then we can select the number of rows where any of these ranks is in the top 10%. We run this and it shows 2.5 million. So the entire table is being returned, which is 10 million rows, and then we filter out all but 2.5 million rows. That's a lot of rows to return just to filter them out. How can we improve this? We can actually move the filtering to the temporary table, so the temporary table would only have the authors that are in the top 10%. Let's update the temporary table. First, we'll drop the table we already created. Then we add the where clause to the select query inside the temporary table. We can create this and see that it is completed. Now in our main query, we can remove this where clause as it's already being filtered. In the execution plan, we can see the cost is now 3.6 million. This has changed because there is less data being returned. We can run the query and see our results here. This query took 26 seconds, which is our fastest result so far. I think we can do better. If we look at our query, we have a subquery which is checking the author Steam ID in another table. This is essentially the same thing as a join. I find it easier to read in these situations to use joins instead of subqueries. We may also get a performance increase if we change this to a join, or MySQL may work out the queries are the same and show no difference. Let's try it. We update the query to use an inner join and remove the subquery. We can check the execution plan, which shows about 4.7 million. Let's run the query. It has completed in 410 seconds, which is 367 plus 43 here. We can see in the results here that we now have more than one row for each review. For some reason, we have duplicate rows. This is not ideal. We could add a distinct keyword, but it would be better to find the source of the duplicates, so we bring less data back and improve performance. Why would there be duplicates here? There are no duplicates in the Steam reviews table as that's the source of data. What about the top authors table? Let's do a quick select star on this. We do this and see some author ID values are duplicated. How many do we have in the table? We can write a query to find the number of rows in the table and the number of unique author IDs in the table. We can see that there are 2.5 million total rows in the table and there are 1.4 million unique author IDs. The reason we have duplicates, or more than one author is in this table, is because we have 3 separate criteria, and it's possible for an author to meet more than one criteria and therefore be in the table more than once. How can we prevent this? We can add the word distinct to the query that creates a temporary table. Generally, we want to avoid using this keyword, but in this case I think it's the right thing to do because we actually want to get the unique rows. So we add distinct and recreate the table. Let's run our main query again. We do this and it completes in 259 seconds. It's better than the previous value of 410 seconds, but still pretty slow. What does the execution plan look like? We get data from 2 tables for our query, then order the data. We have a non-unique key lookup and a full table scan. Why is that? Is there a way we can use an index here? Well, we created an index on some tables, but we didn't create any indexes on this temporary table. We are allowed to create indexes on these tables, so let's try that. We'll create an index on the author Steam ID in the top authors table, as that's in the join. Once we do this, we can check the execution plan again. We have a cost of 2.4 million. We can see that the order has also been changed. The green box refers to the top author's temp table with an alias of A and uses an index. The red box is the Steam reviews table. Let's run the query. It has completed in 21 seconds and shows the right results. So it has improved quite a bit from the previous query, but still far away from our target of 3 seconds. Is there anything else we can do? Well, we have created a temporary table for the top authors. What if we created another temporary table that had the columns we needed, after the join has been done to the top authors table, and after the rows have been filtered to only English reviews with more than one vote? So essentially putting all of the logic into a temporary table creation, and then our main query would be much simpler. Let's try that now. We'll create this temp table called Steam Reviews Top Authors. It's the same query as we just saw in our main query, except for the ordering of the results. We can create this temporary table. Now our main query becomes simpler. We just select the columns in the table and order the results. The execution plan shows a cost of $973,000, which is low compared to our previous queries. We run the query and our results are shown. The query took 5 seconds to run. So we're getting faster with the query, but it's still not quite under 3 seconds. We've used temporary tables so far. These are handy, but they need to be populated within the same session for the user. There is another approach we can take. If this was a real project, we would want to find out how up-to-date the review and author calculations need to be. We could ask the project representative or the stakeholder if it's okay for there to be a little delay in the calculations, such as an overnight recalculation. Let's assume that we do that and they say yes. Why is this important? Because it allows us to use another strategy. We can create a table called a staging table. This staging table can be populated with the results of a complex select query, which includes our calculations and filtering, just like our temporary table. However, the main difference is that the data is kept in the table. This means we can set up a scheduled job or another process to update this data. Then our main query for our report can simply select from this table. Let's try that now. We drop our earlier temporary table for the top authors and then create a new table with the same name, but it will be a regular table instead. We run this and it is created. We can do the same for our main Steam Reviews Top Authors table, which is what our main query will work from. We now have the table created and populated. Let's check the main query again. We can see the execution plan here, which shows a cost of $657,000. We can run this query. It has completed in 4.7 seconds. So it's a little faster than a temporary table, and the staging table can be populated independent of us generating the report. So here are the results of our recent query. We're seeing a lot of data here. In fact, this query returns 599,000 rows. If we're generating a report to show on a web page, we probably don't need to get all of those rows at once. Could we ask the stakeholders if we can show them a smaller set of results and give them the ability to go to the next page? If we assume the answer is no, then I think we're stuck with this query. We have a couple of staging tables and a simpler query that takes our runtime to about 4.7 seconds. So we haven't met our goal of getting it to run in under 3 seconds. If we assume our answer is yes, then we can implement a technique called pagination. This means we return one page of results at a time. We can determine how many to return or how many we just want to show on a page and then return that. Let's say one page of results is 100 records. So let's update our SQL query to use this pagination and return 100 rows at a time. We do this in MySQL by using the words limit and offset. Limit is the number of rows to return and the offset is the starting position. For us, the limit is 100 and the offset is 0, which means show the first page. For the second page, the offset will be 100, and for the third page, the offset is 200, and so on. These can be passed as parameters to the query when they are run by the application, but for our purposes, we can show the first page. Before we run this, there are two things to remember. I've created a video about this concept in more detail, which you can watch here, and what issues they solve, but I'll show you what they are in this query. First, we add a unique value to our order by clause so that we don't lose records in our results set. Then we create an index on the columns in the order by clause, which will improve the performance for the higher number of pages. Now our query is ready. We can check the execution plan and see the cost is $80,000. We can run the query and it has completed in 0.0135 seconds, or about 1/100th of a second. This is the fastest we've seen so far, and we've met the goal of under 3 seconds. One drawback of pagination is that it can get slower for later pages. Let's try this query again for other pages. We change the offset to 100 to view page 2. We run this and it has completed in 0.03 seconds. We change the offset to 1000, which is page 11. The query runs in 0.13 seconds. We can even change it to 20,000 and run the query, which runs in 1.9 seconds. So with this pagination method, the queries still run in under 3 seconds. So how did we go with getting our query to run in under 3 seconds? Our original query completed in 186 seconds. We added some indexes which changed the runtime to 181 seconds. Then we combined our subqueries into a single query, changing the runtime to 272 seconds. We created a temporary table and then added the filtering to that, which meant a runtime of 26 seconds. We used a join and then removed duplicates, giving us a runtime of 259 seconds. When we used a single temporary table, we got a runtime of 5 seconds. Then we used the staging table and had a runtime of 4.7 seconds. Finally, we added the concept of pagination, bringing our runtime to about 0.02 seconds for the first page and increasing for further pages. We assumed we could do pagination, which means yes, we have met our goal. But if we can't paginate our results and need to return everything, then we have a runtime of 4.7 seconds and we didn't get to our target. There are a few things we've learned here. Indexes can help and can be a good starting point, but they don't solve everything. We can combine separate subqueries into a single query, which can simplify our query and help with performance. Temporary tables can help, but they need to be populated, which can sometimes not make a difference to our performance. We can sometimes use a staging table, which complicates the design a little, but it can help with performance. And if we have other ideas of ways we can improve performance, we can often go back to stakeholders to propose an alternative or a compromise, such as accepting an overnight delay in numbers to have a bigger increase on performance. If you're thinking, this has been helpful for MySQL, but I want to see how it performs in another database, then stay tuned for the next video where I'll show you a similar process on the same set of data for another database. Do you have any advice or techniques to improve this query? Is there anything I've done incorrectly or mistakes I've made? Let me know in the comments below. Thanks for watching.